Okay, oh, that's working. All right, so hello, I see some faces that I know here today, so that's good. I have some, people in the audience that can clap for me, even if I say something stupid. Okay, so the talk today is I expanded it into the R and Python ecosystem, so I was curious who here, I mean, I don't want to pigeonhole people into R or Python, but do people have, like, could you raise your hand if R is your main language? Okay, and then how about Python? Oh, it's about half and half. Okay, good. Any other languages that you want to share? Julia? Okay, no. All right, so yeah, so this is for R and Python users, so I'm glad that you're both here. So Kevin just said a little bit about who I am, and some of you already know who I am, but right now I work as a statistician and machine learning scientist at H2O AI, which is a company in Mountain View, California. And the main thing that we do there is produce open source machine learning software that's meant for like big data and scalable machine learning. So, but kind of the idea, if you're familiar with Python Scikitlearn or R caret package, the idea is to produce a platform or just sort of a library that has a bunch of different machine learning algorithms. So instead of just using one library with one certain amount of conventions over here and another library for something else, we have like all of them together that kind of work in the same way. So Kevin already said this as well. I have a PhD in biostatistics from here, Berkeley, and then I've worked as a data scientist at a few different startups, and then I've written a few machine learning software packages, mostly in R. But I do both R and Python. But as a statistician, I guess I'm more of an R primary person. Okay, so this is just the outline. So I'm first going to say a little bit more about what H2O is and who we are. And then the H2O platform, I'll just kind of describe what the point of it is, like how is it different from Scikit-learn or some of the R libraries. And then I'm going to talk about the R API and the Python API. And if we have time, I'll say a little bit about this project called H2O Ensemble, which is a project that I work on, and it's something that I worked on when I was doing my PhD here. And so that's kind of, that's how I got involved using H2O was I needed a platform that had scalable machine learning algorithms and had a bunch of them with the same interface. And so, because I wanted to build a scalable ensemble machine learner. And the only packages that currently existed for that at the time were R packages. And I made some effort into trying to make them a little bit more scalable, but eventually opted for this route. And then we're going to, I guess I was going to try to go over either an R or Python Jupyter Notebook, because I have both with the same examples. But since it's very even, I don't know, maybe you guys could like fight, and then we'll decide like which one we'll go over. Anyway, but they're both available and they're both on GitHub. So if you want to look over one of them while I'm going over the other, you can do that. Okay, so just a little bit more about the company and what we do. So it's been around since 2012, and I think the first time I used H2O was maybe 2013. And my first experience with it was doing a big benchmarking project to compare the random forest algorithm in Scikit-learn and R and a proprietary algorithm called WiseRF, which is Josh Bloom's company, who many of you may know. I used to work there as well. And the sort of fourth one that we benchmarked was H2O. And Wise actually did the best, but H2O was not too far behind. But both of them sort of blew the R and Python native implementations out of the water a little bit. So yeah, H2O is the name of a company. It's also the name of the software. And I'll say more about the software on the next slides. Oh, and then I wanted to mention that we have this Scientific Advisory Council. They are, from Stanford, so that's a little controversial. But if you're a machine learning person, you could probably, move beyond that. And because Trevor Hastie and Rob Tibshirani are both very well known in the machine learning community, and Stephen Boyd is there. So they're both more on the statistician side of things. Stephen Boyd is more on the CS side of things, but he's also a big optimization and machine learning guy. So anyway, these are the people that we work with, and a lot of the algorithms that we have are algorithms that they came up with, and they helped us figure out how to implement in a distributed fashion. Okay, so I think the right way to think about H2O is that it's a platform. It's not just like a machine learning library. It's actually a set of machine learning libraries in different languages. And but the main sort of piece of software that is the core to all of H2O is written in Java, and then all the other APIs just communicate with this main Java library. So it's not just machine learning, though. It's sort of like the reason I call it a platform is because it has this distributed data frame structure as well. So the way that the algorithms work is that H2O has something called an H2O frame, which is just a distributed data frame. So different rows of a data set would be on different machines. And the algorithms work on just chunks of the data at a time. Okay, so this is just a summary slide. So one other thing I didn't mention yet is that it's a platform in the sense that like Spark is a platform and Hadoop is a platform. And the idea is that H2O is, originally when it was developed, Hadoop was really popular. So that was only like 4 years ago, and now Spark is probably much more popular. So originally it was meant to be like a machine learning library for Hadoop, and now we've rewritten it so that it will also work with Spark. And so there's like tight integration between those two systems. And the idea is that you shouldn't have to like move your data into this other place and do the machine learning there when your data lives in the Hadoop file system or in Spark. And yeah, so moving data around is like a big problem with big data because it takes a long time to move around, and writing back and forth to disk is slow. So here's kind of the full list of the APIs that we have. So there's R, Python, Scala. Java is not listed up there, but I mean, the library is in Java. And then there's actually REST and JSON is how the H2O Java library communicates with all the other APIs. So basically, when you're typing in a command in R that says train this model on this data set, it translates that into a REST command and sends it over TCP to the H2O cluster in Java, and then it does what it needs to do, and then it communicates back like what the results were. And the idea is that it's not sending the data ever over in between R or Python or any of these places. The data just lives in Java or in a cluster running on Java. So, and then because we have this REST API, we can also add a front end on it. So there's like a web interface as well. So that's also something that people it's one of the only platforms that actually has a GUI, but also has like the more hardcore stuff as well. So a lot of times things will just be a GUI, or it will be only on the cloud or something like that. So, so we have all different levels of users, or all different levels of skill sets of people that are using this. Okay, so this is just kind of the philosophy of H2O. So the idea is you shouldn't have to sample your data to do machine learning. So one of the first approaches to doing machine learning on Hadoop was a project called Mahout. And the way that worked was they just basically, like for their random forest algorithm, for example, they would, instead of training a tree on the full data set, it would just train it on like the local data on whatever node. So you didn't really have like the full access to the data in the same way that H2O does. So you're essentially doing machine learning on big data, but you're sampling. So the whole point of big data is to be able to use all of it. So the other thing is that it's all in memory, all the computation, so it's fast. I mean, a lot of machine learning libraries work that way, so that's not super unique, but it's all in memory. And another philosophy that we have is kind of using all of the most cutting edge algorithms and trying to really iterate on our software quickly. And so we do a release every like 2 weeks or so, and usually there's a lot of new stuff. So it's kind of like a fast moving target, which is actually one thing that people sometimes don't like about it, is that things are changing so fast that, if you blink your eyes, like things might not be the same. And then this is a list of just kind of the algorithms that we have right now. There's some that are sort of off this list, but so we have coverage of kind of like the main popular machine learning algorithms like random forest and GBM, gradient boosting machine, GLM, and then we have a multi-layer feed-forward artificial neural network, which is just one particular type of deep neural net. So there's a whole bunch of different types of deep learning algorithms, and we have one implemented right now, but that's something that we're going to expand. So on that topic, all of our algorithms are written for CPUs, and so a lot of the deep learning algorithms that exist right now, like CNNs or RNNs, so convolutional neural networks or recurrent neural networks, kind of work better on GPUs. And so before we expand our deep learning coverage, we will be implementing some sort of new piece of functionality that will allow you to use H2O on GPUs. And hopefully it will be doing that this summer. But a lot of people ask us for particular deep neural nets, and usually we say we have this one, and it works really well if your data kind of looks similar to the data where. So I guess what I'll say is that certain types of input data, like images or video or things like that, those are good with like CNNs or other types of neural nets. So if you have kind of like normal data, then that's where we do well. Okay, and so just a little bit about what the architecture of H2O is. So there's these two concepts. I might just sort of skip the middle one, but H2O cluster is just kind of the name for this Java like multi-node, like it's a Java process running on many nodes at once. So you should just sort of think about it as just a process running on a machine rather than like a physical cluster of machines. It does run on top of a physical cluster, but the H2O cluster is sort of just a concept. And then something that we call the H2O frame, which I've mentioned, is just a distributed data frame. And the columns are distributed. And I guess the one thing that you have to have is that each node must be able to see the entire data set. And what I mean by that is that the way that works is there's something called a distributed key value store, which is just like a distributed hash table. And that just keeps a record of where everything is. And so that is how data is sort of accounted for in the H2O environment. So a popular way to use H2O is on Amazon EC2. So this is kind of like what it was designed for is very like cheap commodity clusters that you either already have or are cheaply available versus like very expensive GPU clusters. So if this is if you're at Berkeley, you probably have access to like a cluster here, so that could be another option. But we have a lot of instructions about how to use it on EC2, if that's something that's interested you. So here's just a picture of what a distributed H2O frame looks like and kind of how you should picture it. So each of these little sections that say Java JVM1 heap. So this is just like would be like a 4-node cluster, possibly with many cores on each node. So here's just the link to the GitHub. So I've mentioned that this is all open source, and it's actually if you guys are kind of savvy, so you might know a little bit about different open source licenses. So this is licensed as Apache 2.0, which is basically what businesses want to see. So there's GPL licenses, which are so the copyleft philosophy, and then there's like MIT, BSD, and Apache, which are more liberal. So this is the sort of most liberal of those licenses. So there's actually other companies that take H2O and just like, steal it or whatever. I guess that's not the right word, but like take it and then build a whole bunch of other stuff on top of it and then like repackage it as some other name. So I just saw one yesterday that was like from Sri Lanka or something, and it's like H2O but not H2O. It's like Bizarro H2O, which is good because that's the whole point, I guess. Okay, so now we'll just talk about, so how do we use this from R or Python? Because that's generally how most of our users are interacting with H2O. It's meant to be accessible to people that are not well-versed in distributed computing, and the idea is that you shouldn't have to learn like every single skill in the like big data world to be able to do machine learning. So it functions just like a normal R or Python library. So first, I'll kind of like alternate between R and Python as we go through the next set of slides. So the R package, basically all it needs is R and Java. And so it runs on all the different operating systems. And you can install it from CRAN. Although we always kind of recommend people to install it from our website because we always have the latest version. So CRAN doesn't like it if you update your packages like too frequently. So sometimes the CRAN version is like a version behind what our stable release is. So, but of course, that probably doesn't matter to most people. So if you're comfortable just installing it from CRAN in RStudio, you could just go ahead and do that. And I kind of mentioned this before, but the whole point is that no computation is performed in R. So you can do things in R like maybe munge your data and like do whatever you need to do and then push that data frame into H2O. But you could also just skip that whole step and go just load the, from CSV or wherever your data is into the H2O cluster, and then you can do a lot of the typical data frame operations both in R and Python. So the idea is not that you have to do all the munging in R and you're still loading this giant data frame into R and then doing the machine learning. The whole idea is to like extend the pipeline as far as possible. So you should be able to do like most of your data science stuff in H2O. So basically we've overloaded all the functions for H2O so all the data frame functions that you would typically be able to do, like subsetting rows and like, taking the mean of a column or whatever it is that you're doing, you can do that with the same syntax in the H2O frame. And the same for Python pandas. So if you have an H2O frame in Python, all the pandas syntax should be pretty much covered. If there's stuff that you ever run into that's not there, just to let us know and we'll add it. But we have most of the functionality covered, I think. So here's like, if you go to this place on our website, this is where it will always have the latest stable release. And so this is really the only line that you need is that install.packages thing. The other thing is just guaranteeing that sort of like overtly installing all the dependencies and stuff and then removing the H2O package if it already is there. So then the Python module, the same kind of deal. You just need Java and Python. So Python 2 and 3 is supported. There's a couple Python module dependencies that you will need. And then works on all the operating systems. And you can either download it from PyPy or from our website. And so that's the link for Python. And so I think this screenshot is like a little bit old, so I think there are 2 more dependencies. I think the futures module is on there for when we added Python 3 support, and another module called 6. Okay, so now back to R. So this is, so the only extra task that you have to do when using H2O is start up an H2O cluster. So you can do that from R, or you can do it outside of R, and then once you start up R, just connect to it. You do that all with the h2o.init command. And you have a lot of different options for this function. You can specify what the max memory size. So if you know about Java, that's like the XMX function, or sorry, XMX flag will specify the max memory for your cluster. So in this case, I'm just saying make an 8 gig cluster, because this is me running this on my laptop. And number of threads equals -1 means use all of the cores. That's another thing that we have to do because of CRAN, because CRAN won't let you ship software that by default will start more than 2 cores. So I don't know why, but so by default it will only start a 2-core cluster unless you change it to n threads equals -1. So what it does is it looks and sees there's also 2 other arguments that might be relevant. So there's an IP address. So if you're not doing this on your local machine, if it's running somewhere else, you would put in an IP and then a port. So by default, it will always start the H2O cluster on the machine where you started it from. So this is just running on my laptop. It says successfully connected to HTTP // basically that's localhost and then port 54321. Okay, and so I'm gonna go over all these functions when we do the IPython notebook. But to sort of introduce you slowly, we'll just put them on the slides first, and then as we're going through the notebook, you'll have seen them once before. So here's just the general way to load data in R. So we've started our H2O cluster using h2o.init, and this second one is the function that I mostly use. So most of my data that I'm dealing with on a day-to-day basis is just, I'm developing the software, so I'm just using sort of example CSV files to test things. I'm not always using a terabyte of data. So usually I'm just loading data from a CSV. So I use this h2o.import file, which will in parallel read your file into the H2O cluster without doing anything in R. You're just basically typing commands in R. And then the other way that I mentioned is if you have some data frame already existing in R and you have a big enough cluster, it's not a big deal to process that data frame in R, then you can do that and then use this as H2O function, which will just send it, basically make a copy of it from R and then push it into H2O, where the copy will actually be much smaller in H2O because it's all compressed and it's very efficiently stored data. So here's just a real simple example of training a GBM, so a gradient boosting machine. So the interface, sort of the basic H2O interface that all the different functions have, will have an X and a Y and a training frame argument. So training frame is just the name of, if you go back to the slide, so that train object in R is actually more like just a pointer to where that exists in the H2O cluster. So that, it's just metadata, really. But it's the way that R knows where things are and what they're called. So we pass in this name train, so that's the H2O frame for training frame. And then Y is just the name of the response variable. So whatever that is in your data set, and then X is just a vector of your predictor names. So you can either specify these by name, by column name, or by index. So that's a little bit different than the standard R machine learning conventions where usually X is actually the data frame and Y might be like just a vector. So then there's an H2O.predict, and so this is the same on all the different methods. So whether you trained a GBM model or a GLM model, there's always just H2O.predict. And then that will give you some predictions. Usually, I'll explain. This is not actually typically what I do. I don't actually usually predict and get the predictions and bring them back into R and look at them. I actually give it a test frame and have H2O calculate all the performance metrics like efficiently for me. So it will calculate, you know, MSE, AUC, R squared, log loss, all the like normal ones that you would think of. However, if you did want to do your own custom performance function, then you could do this, where you get the predictions and you bring them into R, and then you like have some R function that calculates some, you know, custom performance metric. Okay, so there's some like basic plotting stuff that we have. So I will talk a little bit about the GUI as well. So when you start an H2O cluster, it starts a web server, and so if you type in localhost port 54321, it will bring up this thing that we call Flow, which is this GUI browser, and you can like click to upload a data set, click to train a model, and then once you've trained models, it spits out a bunch of plots automatically. So it will, scoring history is just sort of scoring your model as you iterate through the training process. So if you were training a GBM, for example, like a way that you can sort of step through the training process is by number of trees. So it will plot, this is just sort of the default for GBM, I think, so it will plot the number of trees and then the MSE. But so you can plot all these things that you get for free if you just go over to the GUI. So a lot of times I just will train a model in R and then go over to the GUI and then like look at all the plots because they're there automatically. Okay, so then another thing that you might want to do in a machine learning problem is do a grid search. So this is the syntax for doing a grid search in R. So there's a function called H2O.grid, and then you just type in the name of the one of the algorithms that you'd like to do. So this is a deep learning example, and then you pass a list of hyperparameters. So in this case, this first thing, hidden underscore opt, is just different architectures of the hidden layers. So in a neural network, so 200, 200 means there's the input layer of the neural network, then 200 neurons, another 200 neurons, and then the output layer. So yeah, so this is just another model parameter that is specific to deep learning. And then the L1 penalty is another thing you might want to grid over, and that's how you do that. Okay, so then Python, we're just going to quickly go through the same stuff. So this is how you start up an H2O cluster in Python. So import H2O library and then H2O.init. By default, Python will actually start up on all of your cores. So we don't have the CRAN restrictions, so that's a little bit better. And then, sorry, this is what it looks like if you don't have a cluster running. It will look for one on localhost, and if it doesn't find one, it will start up its own. But if you already have a cluster running, it will just sort of print out some metadata about the cluster, like that. Okay, so then, how many of you are familiar with Scikitlearn? Okay, so a lot of you guys are. So this is our Python library is sort of meant to be easy to use if you know Scikitlearn. So has kind of the same sort of Pythonic way of doing things. So the first iteration of our Python API was essentially a clone of the R API, where you type in H2O.gbm and then do that. But then we changed it because it sort of made more sense to do it this way. So now you import whatever estimator you want. So this is the GBM estimator. So import that, and then to train, you first set up the model by defining the different model parameters. So here's just an example of some different parameters that we could do. So when I run that command that says model equals that command, that will just basically not do anything. It will just set up the model. And then to train the model, there's a .train method where you pass in sort of the non-model parameters, like the data parameters. And then it will build a model. And one of the things I kind of like, and sometimes people complain about this, which is interesting, is this progress bar. So you can see exactly how long your model is going to take to run. But there's a lot of people that like email and they're like, how do I get rid of the progress bar? I hate it. So I like it because it gives you some sense of like what you're getting yourself into. Okay, so then, so this is just another aspect of, this is kind of similar to the information that will come up when you go over to the GUI. It will just automatically calculate all these things that you might want to know about your model. And you can also access that in the R Python interface. So if you just print the model, this actually goes all the way down. There's like more stuff, but this is just kind of a snapshot. So those are the performance metrics that it will calculate for a binomial model. So MSE, R squared, log loss, AUC, and Gini. And it will also do, it will also calculate a threshold. So for a binary classification model, it will give you the probabilities, but then it will also basically choose the threshold between 0 and 1 that will maximize your F1 score. That's like the default. So you can change that. So if when you train a model, you get both the probabilities that the outcome is 1 and also what the predicted label is based on this default threshold. Okay, so I think I have just a little bit of time just to mention this project. Since there's some biostat people in the audience, they might be familiar. So H2O Ensemble is a project that implements the superlearner algorithm, which anywhere like pretty much outside of Berkeley is called stacking. So either stacking or superlearning. So those are, it's basically an ensemble machine learning algorithm that takes different algorithms like a GLM and a GBM and a random forest and finds the optimal way to blend them together. So it does that by doing a secondary learning step. So you train all the base models and then you train what's called a meta learner that will figure out what the optimal combination is. And I won't really spend a lot of time explaining how that works, but there's a lot of information about it on my website, which I'll put you, there'll be a link at the end of the talk if you want to learn more about it. But basically, H2O Ensemble is implemented for regression and binary classification. And the two things that I'm working on right now is the Python version of this. So this is right now only in R, and then support for multi-class classification. So this is, it's complete sort of in the R version, but the Python is a work in progress. So let's see. And then if you're curious, why do you use ensembles? Usually it's because you use them when you care about performance over everything else. So if you want the best possible model that you could possibly have, that's going to probably be an ensemble. And of course, they take longer to train because you have to train all of the models instead of just one. So that is sort of the use case for ensembles. Here's a link to the package. It's just in the H2O repository under the H2O-R folder /ensemble. And then on this is kind of like the home page for the project. And so there's a bunch of information, if you go there below, that will tell you what the superlearner is and give you links to training and slides and stuff like that, and then show you how to use the package. Okay. Then I guess I'll just talk a little bit about the interface for a second. So this is basically the setup. With a superlearner, you have to specify what base learners you want to put in the ensemble. So that's your job as the user, is just to come up with a bunch of different models that you want to throw in there, and then you have to specify what the meta learner function is. And so these things right here, you can see they're just strings. But what these strings represent are like particular particular, so the first one is a random forest with a particular set of model parameters. So maybe it's a random forest with like 100 trees and like max depth of 5 or whatnot. And then these other ones, deep learning 1 and 2, those would be just other versions of deep learning. So like maybe one with one type of activation function, maybe one with a different type. And the goal is to get a diverse set of base learners in your library, and that's typically how you're going to get the best performance. So you don't want to just do a big grid search and find like the best 4 models and then just take those together. You kind of want to have a diverse representation of different models with different strengths. And even like GLM, which is typically never the best performing model in the group, is often good to have in there. And you might think, oh, with this one algorithm, it's so much worse than the others, I'm just going to like take it out. And sometimes that actually hurts your performance. So it depends on your data and whether or not GLM could help sort of see things that the other algorithms can't see. And then this is the interface, which looks, the first line is just exactly like all the other H2O algorithms. And then there's the family argument is just describes the task that you're trying to do. If you're trying to do binomial classification or regression, would be Gaussian. And then it has a predict function as well. Okay, so now we're going to do a demo. Any like votes on Python versus R? Anyone? Yeah, do you have a Python? Okay. Oh, okay. I made this a problem for myself, I guess. Okay, wait. First, let me tell you about the data, and then I'll delay deciding for a second. Okay, so the goal in this demo is just this EEG data set where it's a binary outcome. It's to predict whether or not your eyes are open or closed based on EEG signals from your brain using this thing that you can kind of see in this picture, but it's kind of hard to see. It's like this plastic like spider thing that goes on your head and measures your brain signals. And there's 14 EEG channels placed on the head. So I didn't create this data set myself. I just downloaded it from the UCI machine learning archive of data sets. So somebody, made this data set. And then this slide is just kind of here to remind me to mention flow flow is the GUI when I do the demo. So here's the 2 links that you can go to that will send you right to the location of the notebooks, which are on GitHub. But if you want to actually follow along, probably what you should do is, so you could like just go to it on the web, or if you want to actually run it yourself, let's see, you would, you could go to H2O, I'll show you real quick. So if you go to the H2O GitHub, you actually, it'll take you a second to set it up, but you would clone the H2O3 repo. So that is there, and then each of these are inside of the different subfolders. So H2O-Py has all the Python stuff, R has all the R stuff, and there's something called demos, and then they're in there. So if you wanted to run it on your machine, you would first clone the repo, and then I know that you guys are pretty much like experts at Jupyter Notebooks, but I'll just show you how this works. So, okay, so if you type in Jupyter Notebook, not book, okay, notebook, then it will bring up the browser in that directory, and then you can just, there's actually only one Jupyter R notebook, which I made, but there's a bunch of Python notebooks. I hope I'll make some more R versions. So anyway, so this is how you get there. So Okay, so I'm going to, I feel like I should like overcompensate for my like R tendencies, so maybe I'll do Python. But the R people can follow along, and it's exactly the same notebook with just the different commands. So, okay, so let me actually just make this a little bit bigger. Oh, this is the R one, sorry. We should go back. Actually, I think I already have the Python one up. Okay, there we go. Okay, so I might be able to sort of go between both. So this is just shows you how to install H2O, and I'm going to assume that you already have done that, even though I'm sure none of you have, but if you'd like to follow along, you can do that. So this is how to install. So if we move, we've sort of already shown this, like how to start up the H2O cluster. So import H2O, and then do, I think it's already running, so we'll do that. Oops. Okay. All right, so then to download this data, it's not a huge file, so I think you guys should be able to do it over the Wi-Fi, but might take a second. I also have it locally if there's a problem with the Wi-Fi. Okay, so that worked. So this demo just uses a CSV file. So I mentioned that you can use data that's in Hadoop or Spark or other places like S3, but CSVs are easy for demos, so I'm going to do that. So we do h2o.import file, and then we have functions that are similar to pandas or NumPy, where you just do data.shape, and that will give you the dimensions of the matrix, so 14,000 rows and 16 columns. And did that run? Okay. So because I've already run this notebook before, it sometimes doesn't look like I'm doing anything, but this is just printing out the head again. So in this file, we have these things are the 14 EEG locations. So these, if there's any neuroscience people in here, anyone? So these actually represent locations on your head, and the eye detection is just a 0 or 1, whether or not your eyes are closed. And then I added this column called split because it makes it easy to test this data set on a whole bunch of other platforms as well. So this just, I randomly partitioned the data into a training set, a validation set, and a test set. And I will, as I'm going through this, I'll explain what the difference between a validation set and a test set is, because those words are sometimes used to mean different things or the same thing. So, but they actually do mean different things. So, so the way that we'll subset this data set is just by looking at that split column. Okay, so this next series of steps is just to show you how to work with like a data frame in H2O. So it has, again, like all of the Python pandas stuff. So data.columns will just show you the column names. This is how you subset. Can you guys see that? Is that, maybe I should make it a little bit bigger? Yeah, okay. So if you want to subset by columns, you just make a list with the column names, and you're going to do data and then bracket columns. And if you want to look at the head, you just do head. So this is just showing me these 3 columns. If you want to do one column, it's the same idea. And I'm going to skip over the next couple things so that we don't run out of time. But just so you know how to do all of these things, like calculate the unique values in a column or look at the levels in a categorical column, all of this stuff is here. One thing that I will show you, actually both in this notebook and I'll go over to the R notebook, is one thing that you do have to do in H2O, and this is for efficiency reasons. So when H2O loads in the data, it only looks at like a little snapshot of what the data is, and then it will load it in. So from that, it will guess like if this is a numeric column, and if it's numeric, like what kind of numeric column, or is this a categorical column, or something like that. So it'll make a guess as to what the column is, and then it will load the whole thing in. So in this data set, we have the outcome is encoded as zeros and ones. So it will basically guess that that's just a numeric thing, because it has to make sort of the most conservative guess about what it is. So unless you tell it explicitly, which you can do, that it is supposed to be like a categorical column, then it will just basically call it numeric. So in H2O, it's a lot of the reason that it's fast is because we do efficient representations of data. And so if something is just zeros and ones, you want to encode it like in the smallest way possible. So by doing this dot as factor, that will convert it into what's called like a Java enum, or in R it's called a factor. Yeah. What is it called in Python? Is it called, I don't think it's called factor. Is there a name for like a categorical variable in pandas? Does anyone know? Okay, so maybe I don't know if there's a name for it, but the R users will know what a factor is. So a factor is just like a categorical variable. And usually R people don't like factors, because if you load in the DataFrame and it's, by default it will say strings as factors equals true, and then you think you have like all this text, and then it's like all factors and you don't want them. But with machine learning, it actually is beneficial to understand that something is a factor or a categorical variable, because when you have categorical variables, usually the machine learning algorithms underneath the hood are doing, so some algorithms will have to sort of expand that category column. So if there's 3 different categories in your factor column, it will sort of balloon it out into either 2 or 3 columns that are just binary indicators of, was this category A, yes or no? Was this category B, yes or no, et cetera. So GLM and deep learning will do that. And that's not just an H2O thing, that's how those algorithms have to work. But with other algorithms like GBM and random forest, it can actually be more efficient with categorical, so it doesn't like balloon them out like that. So this is something that handling categoricals is not usually done for you by machine learning algorithms. So the name for this process is called one-hot encoding. So you take a categorical and expand it into like the binary representation. So a lot of packages will make you do that by yourself. So it's something to just think about. But let me go over to the R version and show you, sort of go down. So this is what we just saw. And then this is where we are over here. So just making sure that it's a factor. So, and actually if it is, if it's numeric, it will try to do a regression instead of classification. So it's important that you have your data, and it's kind of to force people to make their data efficiently represented. But I do have some like grievances about it, because it's not necessarily, I don't know, a lot of the other machine learning packages kind of just like do that for you and make you not think about it, but we kind of want you to think about it, and I don't know if I 100% agree with that approach. Because a lot of people ask us, how did I get this regression model? I have, binary outcome, and so it might be like more of a user interface thing that we possibly change in the future. But anyway, I spent way too much time on that topic. So we'll go on and we'll train a model. Okay, so all of this is just like general, showing you basically that this is exactly how it works in pandas, and this is exactly how it works in H2O. So the thing that I said I was going to explain is what is the difference between a validation set and a test set. And so a test set is something that you only use once, and it's to evaluate model performance or to estimate model performance. And a validation set is used in a couple different ways. One, it could be used to like tune a model. So if you have some parameter that that you need to choose in a model. Like let's say if it's a GBM, you would maybe like the depth of the tree. So you could try a bunch of different depths of trees and then train a bunch of models and then evaluate them all on the validation set and then like choose one that looks the best, but then you throw away that validation set because you've already learned from it, just like you don't test your model on your training data, you don't test your model on your validation data either. So you actually have to like have a clean data set, the test set that you've never used before to get like an honest estimate of your data. Not everybody always does that because sometimes it's essentially you're overfitting your model. If you were to use, let's say, a test set to choose the model parameters and then evaluate it on that, you're going to overfit your model. But sometimes it's like not the worst thing in the world to do that if you are okay with that. But this is sort of like the proper way to have a train, validation, and test set. Or there's a whole nother thing, cross-validation, which you can also do. But I'll show you that next. But let's train a model finally. Okay, so I've run these. So actually, yeah, I need to specify what x is. So, So x is, I'm just saying, give me, make a copy of the list, which is train.columns, which is the name of the columns. And then I'm going to just get rid of the last two things, because those we're not going to use for prediction. So you remove those. And so now x is just a list of those 14 EEG locations, and y we set it actually a bunch of cells ago up above, but that's the eye detection column. So this will train a model. Okay, so that's done. And now we can inspect the model. So let's see. Before I just gave you a screenshot of what this looks like, but we'll kind of go through all the stuff. So the first thing that we report is the training metrics, which I don't usually care about. I kind of skip over that, and I go down to, actually, let me take a look here. Did we, yeah, so I passed in a validation frame, so it actually also calculates validation metrics. And so I might look at those and think that's like an okay estimate for model performance, because with GBM, there's nothing. I just trained one model with one set of parameters. So in this case, it is functioning like a test set because we haven't used it other than to just calculate these validation metrics. However, there are a lot of, GBM is one of the algorithms that by default won't use, if you pass it a validation set, won't use that to like tune anything automatically. If you turn on something that we have called early stopping, so if you say, I want like 3,000 trees except for stop when the error stops going down, basically. Then if you pass in a validation set, it will use that to decide when to stop, and like maybe it'll stop at 570 trees, and that's just good enough. So a lot of times, if you turn on certain parameters, like early stopping, it will use that validation set to train the model, and then it becomes not good anymore. You have to throw it away, and then you would have to. And so this is not H2O like specific. And the early stopping is, but like the concepts are not H2O specific. It's just machine learning best practices. So it will print out a bunch of stuff which you may or may not care about, and then we can calculate the model performance on a test set. So we can do two things. One, we can generate predictions on a test set and like look at those predictions and maybe do something with them. Or we could just calculate the performance by first, it will get the predictions and then do all the performance metrics. So that's usually the function that I use is, so model was what we called our GBM model, and then model underscore performance takes in like a new data frame, which is called test, and has this thing called like this performance object, which is, it's just each of the there's like binomial, multinomial, and regression model metrics, and they give you different ones. So this was a binomial model, so it will give us particular things. So if you want to actually pull out specific values, you just do that using the like .r squared function, .auc, .msc, and that will let you get those values. And then let's see how we are on time. Okay, I'll try to hurry up. So then the other thing that you might want to do is do cross-validation. So you can actually just copy exactly what we had before and just add this n folds equals 5. And then what it will do is it will train a regular model like it did before, but then it will do 5-fold cross-validation as well. So it will train 5 more models and like evaluate the performance, and then you have like a cross-validated performance metric. So let's just do that. So this is obviously going to take a little bit longer, but it does the n folds in parallel, so it's pretty fast. All right. So that's done, and then you can access different things. So it will have. This is how you get at the cross-validation metrics. By default, it'll return the training metrics, which is also probably because it will always calculate the training metrics. It's not usually the thing that you want, but it's the default. So I showed you in R what the grid search looked like, and I won't run this because I want to leave time for questions, but this is basically how you set up a grid search in Python. So here's the number of trees that we're going to grid, which is actually a very silly thing to grid over, actually, but it's sort of just here for demonstration purposes. So max depth, and then maybe learn rate, and this is just what you do. So there's something called H2O grid search, which is similar to the R version of H2O.grid, and you just pass along the hyperparameters, and you say which thing you want to grid over, which is the gradient boosting estimator, and it's that simple. So then it will do this, it will grid, and then usually the point of grid search is to try out a bunch of different sets of model parameters and then pick which ones are the best. And that's another use for like the validation set rather than the test set. So validation set is good for grid search, basically. So if we want to do that, I'm not going to run this, but basically it just gives you back all the models, and you can sort by this. In this one, I said sort by AUC, and so like this one has 0.96 AUC, and then like if we scroll down to the very bottom, like there's some really bad versions, like 0.67. So this is why it's good to do a grid search, because you don't really ever know beforehand what good learning rate is, what good max depth is, how to, there's a lot of different parameters that you can work with. So then this is just how to sort of piece out what the best model is. You're just saying in this AUC table that I've already sorted up above. So I sorted it and I called it AUC underscore table. And then it's just saying go in the model ID column and grab like the first thing, so 0, and then that's so this is when I mentioned the key value store, so the data frames and the models are all stored by like hashes in the key value store. So this is just the name of the model, which is a key, and we just say to get that model from H2O and make an instance of it in Python or R, you can use this H2O.getModel. And then if you want to look at certain things, it's like bestmodel.auc and et cetera. So that's the rest of that. So I think this, I'll just sort of like scroll through this and let you see the R version. Looks very similar. So this is the same thing that we did, H2O.gbm. Just add the n folds. And this is getting the AUC. This looks similar as well, H2O.grid. And the printing looks a little bit different in Jupyter Notebook between R and Python. Yeah, so this is the same stuff. So let's see. I think I have like one more slide maybe. Oh, yeah, so these are just like all the links to all the different places that you can learn more about H2O. Oh, I did mention that I would talk about flow to you. So flow, let me just do one thing before I stop. So let me pull up, since H2O is already running, there's, this is what flow looks like. So if I want to say, like, get models, like here's all the models that we just trained. These are the default generated names. You can name them things that are easier to read. So if I just click on one of them, this will show just some basic stuff. So the ROC curve, you can change it like with different thresholds. And then it will calculate like the confusion matrix from there. So this is validation metrics, which is usually the one that you care about. It'll do variable importances for GBM and random forest. So we'll show you how important things are. There's some other things like gains and lift tables. And there's a whole bunch of other things that you can kind of click through like that. So if you wanted to, like, this is how you, so here's data. If you wanted to upload a new file, you do that. Modeling, here's all the models that you can do from here. And then there's other things, like this will give you stuff about, like, your, you can download logs and stuff like that if anything breaks. There's this thing called the water meter, which it doesn't work on, it only works on Linux, but what it is it shows you like all of the cores being used. So if you have a huge cluster, you can see actually when your cores are active. There's other like Linux tools that will do this, but this is just like a write in H2O type of thing. Cluster status. I think there's like some quick links to like documentation, etc. So, and then people sometimes compare this to like a Jupyter notebook because it looks kind of the same, but actually it's written in CoffeeScript, and I don't know why, but it is. And you can't execute arbitrary like R commands or Python commands. So that's how it's different from a Jupyter notebook. And people have asked us if we were maybe going to like merge this with Jupyter notebooks or like try to somehow integrate it. And I don't know that we are going to do that or not. But if, I mean, since this is like a good place to ask people about Jupyter notebooks, like if anyone wanted to talk to me about that further, like feel free to do that. It's kind of just meant for people who don't write code. So, but there's a lot of coders who use it who want to be able to interactively like write the R code and then have some stuff come up and then, you know. So we've talked about sort of like merging those together in some sense, but I don't think that we have that planned or anything. So I don't know. So yeah, so this is where to learn more. And we have all these, like, we do a lot of talks and meetups, so we have a lot of recorded video presentations of all of our different algorithms, and we have a lot of like applied talks, so customers or people just in the community that like want to talk about how they're using H2O, and they go to a meetup and talk about it. So there's all these, we're very like involved in the community and in the meetup community especially. So so those are those links. And then there's, if you want to learn more about how we, I maybe didn't mention this, I'm not sure, all of our algorithms are completely written from scratch and they're distributed. So they're, that's part of what H2O is for, is to sort of write these out, rewrite them from scratch so that they work in a distributed fashion. So a lot of the details about how we did that are in these little like booklet things. So at conferences and stuff, we'll print these out and we hand them out to people. But they're also just, the PDF versions can be found at that link. So this will say like how, you know, go into like a lot of detail about how we did the distributed stuff and how our deep learning works and stuff like that. Okay, and then this is how you can get a hold of me if you want to talk about H2O or machine learning or anything else really. And then if you want to learn more about stacking or superlearning, I have some links on my website, which is still stat.berkeley, because I'm not a grown-up. I don't have a real website yet. Maybe I'll get one this year. Seems like the right time. OK, so anyone? So I guess maybe should we stop and then we'll do the questions?